So we want to develop a little more logical, structured way to talk about limits and to analyze limits. So what 1.3, which is what we're going to cover for the next 45 minutes maybe. 1.3 is about properties of limits. So it's going to give us it's going to formalize some of the tools we've been using and give us some new tools to evaluate limits. It's fairly beastly section. Fairly beastly. The first thing, so remember, the idea here is I want to give you new tools so that you can evaluate limits quickly, okay, and structure with some sort of structure. One thing that is good to know is, well, it kind of depends on the definition of a basic function. So we're going to agree that there are certain types of basic functions. And a basic function is pretty much any function you covered in 126 or 127. Pretty much. So we will call any polynomial, rational, exponential, root, exponential, log, or trig function a basic function. So like I said, these are all the functions you talked about in pre-calc. And what happens is, basically, limits behave extremely nicely with basic functions. So what I'm doing here is I'm taking sort of 4 theorems from your book and combining them into one statement. This covers theorems, a bunch of theorems from your section. But this is basically about limits of basic functions. So let f of x be any, suppose I have any basic function. And let c be any value, any x value in the domain of f. Then the limit as x goes to c of your basic function is equal to f of c. So this is making more formal the idea that if you can just plug it in. Right? If it makes sense, you can just plug it in. The idea of if it makes sense is covered by the fact that c is in the domain of the function. Right? Once c is in the domain of the function, then it makes sense to just plug it in. So I'll do some examples, but before that, I want to warn you, this is a lie, because there's one exception to this. Okay. So I gave you all these basic functions: polynomial, rational, exponential, log, trig. This rule works fine for all of those. Okay, and it works fine for root functions, except for one type of root function at one specific point. Okay. So this whole idea is invalid for functions, for root functions with an even index. So we'll say even root functions at x equals 0. Now I'll show you what I mean in a second. Otherwise you're fine. Otherwise you're fine. But so let's do some examples to understand what this is saying. So evaluate each limit. The limit as x goes to 5 of root x. Before, in section 1.2, the logic was, well, if I can plug it in and it makes sense, then just plug it in. That's true. That's still true. But now, you want to do a little more analysis of it. You want to start thinking about it in terms of what properties we have and what theorems we have. You want to say, oh, well, this is a basic function. This is a root function. Root functions behave very well with limits. I can just plug it in. So it's the same idea with a little bit of a logical twist. Right? This is the reason, this theorem is the reason that you're allowed to do this. This works just fine. What about this? This is the exception I was talking about.
Inside the root canonical zone.
Yeah. Well, no, not exactly. Underneath the root can equal 0. That's okay. That's not the problem here. Yeah, there's no left side, right? So this works in general, right? You want to say, oh, this is one of my basic functions. Root functions are cool. I want to just plug in 0. But this happens to be the one exception. It's an even root function at x equals 0. This is the one exception to this rule, right? Because if you think about what the graph looks like here, if you're trying to do the limit as x goes to 0 of this, you need to approach on both sides the same y value. So on the right side, you're approaching 0, which is fine. But on the left side, there's no function. So the left side x values are not approaching anything. So this guy, what's the answer for this? This is another one of those instances where it would be nice to specify, I just want the right side. You know what I mean? What about limit as x goes to 0 of cos x? So trig functions are basic functions. As long as it makes sense, you can plug it in. So you would plug in 0 and say this is equal to cosine of 0. What about tangent, limit of tan x as x goes to pi over 2? This one does not exist. Why is this a problem?
Because the ends of the function are going up and down.
Tangent's a perfectly legit function to plug things into as long as you're plugging in a domain value that makes sense. Right? This is not in the domain of tangent because tangent has an asymptote at pi over 2. So this does not exist. Either you remember that tangent has an asymptote at pi over 2, or you turn it into sine over cosine, and this will give you 0 in the denominator because cosine of pi over 2 is 0. But you want a graph of what's going on. This is tangent. And so I'm asking what happens as x goes to pi over 2. This guy's pi over 2. That's where the asymptote is on tangent. One's going up, one's going down. They're not approaching the same thing at all. So it does not exist. What about ooh, this one always messes people up. Limit as x goes to 12 of 7.
Seven.
7. This is a constant function. This is a constant polynomial, horizontal line.
Y equals 7.
Y equals 7. So no matter what x is going to, this is going to go to 7. Right, so whenever you have a constant here and a limit, that's the result. You need a graph. This is what we're trying to find a limit for. 12 is over here. So we're going with 7. What about the limit as x goes to 25 of e to the x?
Natural log of, no.
2 times 10.
E to the exponent of 25.
It's just e to the 25, right? You can approximate that if you want, but the idea is e to the x is one of our basic functions, so we can just plug it in, and that's our answer. Huge number. Huge number. Okay. We don't need any more. So as long as you have a nice function that you're used to working with, unless it's root x at x equals 0, right, as long as you have a nice function you're used to working with, you can plug things in. Okay. The next, well, questions about any of these? The next kind of property, this first property was limits behave well with basic functions. Okay. So if you have any of the functions that we had in 126, 127, limits are going to behave fine with those as long as you have a good domain value. The next property is that limits behave well with our basic operations. So this is technically in this section. This is 2, but I don't really care about numbers. Limits behave well with operations. So what do I mean by operations? What are our basic operations? Plus minus times divide. Right. So here's how this works. Suppose you know the limit of some function f as x goes to c. And you know the limit of some function g as x goes to c. Then you know the limit of f plus g, f minus g, f times g divided by g. So kind of the result here is then if you want to know the limit as x goes to c of f of x plus g of x, it's just going to be this limit plus this limit. I don't particularly like writing it that way. The way I think about this is that your limit distributes, just like normal multiplication might.
Is that always true?
Oh yeah. Oh, yeah. As long as it's plus, and as long as these limits exist, these limits have to exist. If these limits don't exist, it doesn't make sense. Okay. But if these limits exist, then the limit can distribute across a plus n. So at the end of the day, you just get L plus n. Whatever the limit of f is plus whatever the limit of g is. There's no exception for this. And if you put a minus down here, if it's minus instead of plus, all that changes is that this becomes a minus and this becomes a minus. Similar things for multiplication and division. If you have f of x times g of x, the limit goes to both of them. So the overall result is whatever this limit was times whatever this limit was. And division. The one thing you have to be careful on division, what do you always have to be careful of on division?
Bottom 0.
Having the denominator equal 0. Right, so this limit when you divide makes sense and it distributes, so it goes to the top and it goes to the bottom. So overall you'll just get L divided by M, you'll just get whatever the first limit was divided by whatever the second limit was, as long as M is not 0. If M equals 0, this isn't valid. So let me give you an example or two. There's one kind of extension to this. Right, if you have, instead of a function times another function, if you have a constant, like the limit as x goes to c of some constant k times the function f, what do you think happens with that?
K L.
Yeah, you can still do the limit. You can do the limit of k and you can do the limit of f. But the limit of k, since it's a constant, is just k again. So this guy ends up being k times the limit of f, which is kf. Let me give you an example. So suppose you know that the limit as x goes to 5 of f of x equals 2, and the limit as x goes to 5 of g of x equals -3. So you have this information somehow, maybe from a graph, maybe from a table. Somehow you have this information. Then let's figure out what the limit as x goes to 5 of 10 f of x plus 7 g of x times f of x. So basically what all of these rules are saying is that if you have one of your 4 basic operations, you can just push the limit inside. You can just push the limit past the 10. You can push the limit over to the g and over to the f. Okay, because there's a plus, so you can do it between the plus, and then there's times, so you can do it between the times. So if I were doing this out in gory detail, I would start with doing the limit to each of these, like this. See what I did there? Oops, C is fine. Because of this rule right here, I'm able to push the limit into each of them. And then each of these I have another rule for. This is a constant multiple, so it comes out. This is all multiplication, and this is a constant multiple. The constant multiple will come out, and then you'll push the limit to each one. And now you can plug in. Now you know what all this is. Limit as x goes to 5 of f of x, 2. Right? That's what you were trying to simplify to one of these, because that's all you know. So this 10 will stay, but this will be times 2 plus 7 times the limit of g is -3. The limit of f is 2. 20 minus 42, -22. Sometimes in math, it's okay to push things through to each term or to each factor like this, and sometimes it's not. Right, so what this is saying is limits behave really nicely. You can always push them through operations. Can you think of something that doesn't behave nicely? What's something that you can't do this to, distribute across a plus sign?
I'm sorry, say that again.
I'm telling you, in this particular part of 1.3, is that limits can be pushed across plus signs, distributed across plus signs. I'm asking you, is there anything in math, anything you know of in math that doesn't work for?
Exponential.
Exponents. Doesn't work for exponents. That's one of the main examples. And if I gave you something like x plus, no, let's not even do x, 2 plus 3 squared, you cannot distribute this across the plus. This is not the same thing as 2 squared plus 3 squared. Or roots. Roots don't work either, right? If I gave you root 2 plus 3, that's not root 2 plus root 3. So what this is saying is that limits don't have that problem. You can push them across, you can distribute them across plus signs, multiplication signs, whatever you want. They work really well. Huh. Oh, I have one more example for this idea. Okay. Here's two functions. This guy's going to go like this, and he'll have a hole here. I'll come back there. We'll call this guy F. And here's another function. He's going to have a vertical asymptote at 0. Oh, no, not at 0, a -1. Maybe he looks like this. With that. So he's missing a hole at 0. Or there's a hole at 0 and the point's filled in upward. This is G. I want you to find for me the limit as x goes to 0 of 10 f of x divided by 3g of x.
Doesn't exist. Negative 10.
Wait, it doesn't exist or negative 10?
I don't know. I think it doesn't exist because g of x is on the bottom.
So g of x is in the bottom. And so that would be bad
No, but is
if
that
you
a-
were going to 0.
Is that a dot in there?
It doesn't matter, but it is. But I'm dealing with limits, right?
Yep.
Okay. So what I can do is push this limit right next to the function, right? Limits behave really well with division and multiplication. So I just need to find what 10 times the limit of f is as x goes to 0, and divide that by 3 times the limit of g as x goes to 0. So on the top here, the limit as x goes to 0 of f of x, as x goes to 0, f of x is going to 3. So the top will become 10 times 3, which is 30. On the bottom, I can just conquer the g limit now. As x goes to 0 on the g function, again, we're dealing with limits. So I'm looking at the trend. So what's the trend? What are the y values approaching? They're approaching -1. Does that make sense? So on the bottom, I'll get 3 times -1. So 30 over -3. So that for this particular topic, you can push the limits and distribute them, and you can move them right next to the function. Composition. So here's another property. This is the 1.5. We're going to do this. Suppose f and g are functions that satisfy whatever, some condition. Basically, this condition is saying that f and g are continuous. But you don't know what continuous means yet, so you have to spell it out. I'm never going to call you on this, okay? I'm never going to make you remember this or even really understand what this means. You can read it and try to figure it out if you want. But I want two functions where when I go to C, I get L out of my G function, and then in another function when I go to L, I can just plug it in and get f of L. If that's the case, then the limit can be squeezed right past f. So this is composition when you plug one function into another function. And if I were going to sum this up here, basically if you have nice functions or nice basic functions, you can squeeze the limit past the first function. So you can rewrite this as f of the limit as x goes to c of g of x. Because this was equal to L, this is equal to f. So instead of trying to unravel this cryptic stuff here, let's just do examples. Example. Find the limit as x goes to 0 of cosine of root x. So again, this is basically saying, just plug it in. But instead, the way we're sort of rephrasing this so that you get used to these limit properties is, you can push this limit past the cosine. Right? You can just slip the limit right inside because cosine is such a nice function. Oh, that's right, this does not exist. So you can try this, but then what would happen? This limit does not exist. So the overall limit does not exist. That's not what I want to happen, but you're right, absolutely.
Maybe x to 1.
Yeah. So if we change this to any other positive x value, so this one doesn't exist because of that problem with square root. But let's do pi over 4. Oh no, because we can do the root. Let's do 1. So this guy, actually it's not. I don't think anyway. The same principle applies, you know, when you have a composition, since the root is inside the cosine, you can squeeze the limit in. But now this works out. 1 can be plugged in here because root x has a left, you know, it doesn't end at 1. So you plug the 1 in here, and you get cosine of root 1, which is just cosine of 1. Cosine of 1 radian is, I don't know. If this were pi over 2, it would be 0. So what about something like, maybe one more. Limit as x goes to, what have I got here for you? 2 of sine pi over root x plus 1 to the 4th plus x pi over 9. This is kind of combining everything we've learned. What do you think the moral of the story is here, or what? How should you approach this? So if it's a basic function and if it's a basic operation, limits just blow right past them. Okay? This limit as x goes to 2 can be pushed inside the sign, and even more than that, it can be pushed inside the denominator and inside the square root, and you can plug it right in. And it can be distributed over here, and you can plug it right in. So this is equal to sine of pi over root 2 plus 1 to the 4th plus 2 pi over 9. You can just push the limit right in until you get up to that. What's that equal? Something. Well, 2 plus 1 is 3. Square root of 3 to the 4th, you guys know what that is? No? Square root of 3 times square root of 3 times square root of 3 times square root of 3? Yeah, 3 times 3. So sine of pi over 9 plus 2 pi over 9. Sine of 3 pi over 9. 3 pi over 9 is pi over 3. Sine of pi over 3. So I spent, it's about 10 minutes, I'll use it, I'm just that kind of guy. But I spent basically 40 minutes telling you what you already knew. If you can plug it in, do it. Bottom line. There's a bunch of rules, there's a bunch of fancy theorems, and if you ever go farther in math, you'll probably need to learn them a little better. But for most of the purposes, to get to the answer, if you can plug it in, do it. No matter how ugly it is. So what we're going to spend the rest of this chapter on is when you can't plug it in. Because it's easy when you can. So we get to our first indeterminate form, which you guys have already noticed. So an indeterminate form is basically, there's a couple of them. The one we're going to talk about is 0 over 0. So when you plug in your x value into your limit and you get 0 over 0, you cannot say what that limit is right away. You need more analysis. Okay? Right, so for example, if I give you the limit as x goes to 2, let me do 0 of x squared plus 2x over x versus the limit as x goes to 0 of x squared plus 3x over x. If you try to directly plug in 0, you get an indeterminate form. Okay, you get 0 on top, right, because 0 squared plus 0 is 0, and you get 0 on bottom. Same thing here. If you try to just plug in 0, you get what we call an indeterminate form. The reason I'm showing you this is because these actually have two different answers. Right? What's the limit on top? It's 2. Right? Because you can factor. This is equal to the limit as x goes to 0 of x times x plus 2 over x. Once you cancel your x's, then you can plug in the 0 because you don't have this indeterminate form. Right now there's no 0 in the denominator, so when you plug in 0, you get 2. Whereas over here, if you pull the exact same trick, factor out the x plus, or factor out the x, the x's cancel again, but when you plug in 0, you get 3. So the idea behind an indeterminate form is it's some indication that that limit cannot be determined without further analysis. There's kind of 3 further analysis we're going to learn, and I don't have time for all of them. Maybe I'll just do the first one and the other 2 for next time. But there's 3 things you can do if you try to plug in and you get this indeterminate form. The 3 techniques for dealing with 0 over 0. At least for now. One, factor and simplify. So that's what we've been doing when we got 0 over 0. If possible, factor both the numerator and denominator and simplify out one of the factors so that your 0 goes away in the denominator. Second option, you can rationalize. Either the numerator or denominator. Do you know what rationalizing means? So rationalizing means multiplying by the conjugate so you can get rid of the root in the top or the bottom. So I'll do an example of that. Then the third situation, where you get 0 over 0, are special trig limits. So there are two specific special trig limits that you run into every now and then in this chapter and in this book, in calculus. So I'll go over these a little bit more next time, but I'll write them for you so you have them here. The limit as theta goes to 0 of sine theta over theta. Right? If you plug in 0, you get sine of 0, which is 0, and 0. So this is an indeterminate form. This is equal to 1, actually. So this is kind of just something that has to be memorized. I'll show you why next time. And then the other one is the limit as x theta goes to 0 of 1 minus cos theta over theta. So in this section, if you ever are trying to evaluate things and you end up with 0 over 0, you have to do one of these things. Let me show you this one, because we've done this one quite a bit. Okay, let me show you this one, and then on Monday I'll come back and do one of these for you. But I'll do one example, rationalize, and then we'll call it a day. So evaluate limit as x goes to 3, root x plus 1, minus 2 over x minus 2. So first observation, the first thing I would always try whenever I'm going to evaluate a limit, plug it in. What do you get? 0 over 0, right? So then, okay. Boo, we hate that, but it happens. So I try to plug in 3 on top, and I get 2 minus 2, which is 0. I plug in 3 on bottom, I get 3 minus 3, which is 0. Okay. So now I'm going to have to use one of these techniques. Factor and simplify doesn't really make any sense here. What's there to factor? I mean, you can't factor x minus 3. That's broken down. Maybe you can find some sneaky way to factor this, but it's not the obvious thing to do. Okay, the obvious thing to do when you have a root is to multiply by the conjugate and try to move that root. So what I'm going to do, whenever I get into this indeterminate form with roots, I'm probably going to try to rationalize. So in this particular case, because I have root minus 2, root x plus 1 minus 2, I'm going to multiply top and bottom by what? Plus 2. You change the sign in the middle. So I multiply all of this times this. Some advice. You're not going to want to multiply out the denominator here. Because our whole hope is that this 0 goes away. That this x minus 3 goes away. Right? Because x minus 3 is giving us 0 in the denominator when we plug it in. So we're hoping this cancels. So don't multiply it out, because then you won't see how it cancels. But you do want to multiply on top right now, because that's going to get rid of the root. So do you guys know what you get on top here?
X minus 2.
It's true. So when you multiply by the conjugate like this, it ends up being this guy squared minus this guy squared. And if you don't remember that, you could FOIL it out. And you'd have to do this times this, this times this, this times this, this times this. So the x plus 1 times x plus 1 is obvious. So I'm sorry, root x plus 1 times root x plus 1 is obvious because it gets rid of the root. The root x plus 1 times the 2 and the root x plus 1 times the negative 2 are going to cancel. So because one's plus and one's minus, they're going to cancel. I'm not even going to write it. So the only thing left to do is negative 2 times positive 2. Minus 4. On the bottom, leave it as it is.
But they don't know the same thing.
It's limited as x versus 3.
Oh, 3. If it were 1, we wouldn't we need to do this. So how did that help us?
In no way.
Oh, maybe.
Is it still gonna be 0 over 0? Oh, yeah, no. Yeah, never mind. Sorry.
Yeah, so you do still get 0 over 0 if you go right to plugging in. Right? But if you simplify this a little to x minus 3, and you see that there's an x minus 3 on the bottom, the x minus 3 is canceled.
And you get 1 over 4.
Now you can plug it in. Right now, because the x minus 3's went away, when you plug in 3, you'll get 1 on top, because there's always a 1 sitting up there, over root 3 plus 1 plus 2. I'm out of time. I will do some, I'll answer questions without any homework. Start, look at 1.1, do 1.2, start 1.3, you can do a lot of 1.3. And ask me questions on Monday. I'll finish up 1.3 and start 1.4.